In this video, we're going to explore how partial derivatives can be applied to a chemistry concept, the ideal gas law. One of the formulations for the ideal gas law is that the pressure of a gas can be related back to the amount of gas in numbers of moles, an ideal gas constant, and the current temperature and volume of that gas. We're going to consider a simple example where we're dealing with 1 mole of gas, and we're going to look at the partial derivatives of pressure with respect to temperature and pressure with respect to volume. And here we're also going to be able to dive in a little bit deeper and look at the units of those partial derivatives. To compute these derivatives, it'll be easier if we include our 1 mole here, and if we also capture another element of this calculation, which is that the v in the denominator is more easily expressed for derivative calculations as a negative exponent. So this is the same pressure calculation here with the 1 mole and the v expressed as a power. With that formulation, we can calculate the derivatives. If we focus on t as our starting point here as the variable of interest, then both r and volume are going to be constants. We'll have r times the other constant v to the negative 1, and then the derivative is only taken of the t's, the temperatures, and the derivative of temperature with temperature is just 1, and so we end up with r over v. If we take the derivative now of the same formula, but with respect to volume, this time the constants are r and t, and the volume to the power negative 1, when we differentiate it, we get negative v to the negative 2. Bring down the power, subtract 1 from the power. And we would typically write that as a fraction negative RT over v squared. Now what about the units? Well, if we're talking about pressure with respect to temperature, we can do the same formulations we did with single variables, which is recognize that the units of this derivative are the same as the units of the ratio of pressure to temperature. So degrees Kelvin per, pressure is kilopascals. Kilopascals per temperature degrees Kelvin. In comparison, if we take the partial derivative of pressure with respect to volume, that will be kilopascals change for every unit of liters, which is our unit of volume here. And that's it. So we can interpret these, as we will shortly, as how much does the pressure change when the temperature increases, and how much does the pressure change if the volume is increased, and we can get more specific with these units included. We can actually compute values for those derivatives now, and we're going to do that at a 300 degree Kelvin, so about room temperature, 10 liters of gas in 1 mole, and we're going to use the ideal gas constant suited to the units we have selected. So in that scenario, our rate of change of pressure with temperature is going to equal, going back a page, simply r over v, and we have the values for both of those, and so that would be 0.831, again units, kilopascals per degree Kelvin, and looking at the rate of change of pressure with respect to volume, we're going to have, from the last page, negative RT over V squared, negative RT over V squared, and that's going to, with the values given to us, equal negative 8.31 rather. Here the temperature plays a role, it's 300, and the volume squared, 10 squared. This calculation is a little more involved, so we grab our calculator, and we end up with approximately negative 24 kilopascals per volume unit, which is per liter. Last but not least, what do these actually mean? Well, we found the derivative of pressure with respect to temperature was 0.831 kilopascals per degree Kelvin. And what that indicates is, for 1 mole of gas, we'll put all the details in this, for 1 mole of gas, currently at 300 degrees Kelvin and with 10 liters of volume, if we increase the pressure if we increase the temperature, that's the independent variable here, and again notice the default of increasing the independent variable, T, the pressure will increase, and we know it's an increase because this is a positive quantity. So our pressure will increase by this rate, by approximately 0.831 kilopascals for every degree, or per degree Kelvin of increase. Degree Kelvin of increase. So again, the idea of the derivative in multivariate is the same as in single variable. This is exactly the kind of sentence we would have expressed for a single variable derivative. The subtext that we have to include here is assuming all other values, in particular here, assuming the volume remains constant. And that's capturing what we do in the mathematical operation, which is treating V as a constant when we're taking the partial derivative with respect to temperature. And likewise, the volume partial derivative indicates that for an increase in volume, if everything else stays constant, the pressure will decrease by, let's go back to the value we found on the last page, it'll decrease by approximately 24 kilopascals, and we just say decrease by 24 kilopascals per liter of volume increase. And there we are. So notice we talked about a decrease here because the sign in front of the derivative for the volume partial derivative was negative. And so what we're getting is a representation of what we understand about gases, is that if we increase the volume that the gas is contained in, the pressure is going to go down. Already itemized and even made more quantitative with this specific value here for the scenario we're looking at.